Hello everyone, my name is Raymond Hinahan, and this is my presentation for my internship held at Baywar Systems Center Pacific. Sorry I couldn't be there tonight for Mesa Night, as I am currently in Irvine getting for school next week. So a little bit about myself. I conducted this internship from June 20th to August 31st, and I am a Southwestern college student who just transferred to UCI for this following quarter, and I am studying electrical engineering with the hopes of eventually attaining a master's. So, why Spaywar? Well, I've heard plenty about the company from friends and family, and I knew they were close with the Navy. And since they were government related, I deduced that they were up to date with the new technology, and because of this, I would get skills and experience to further my career in engineering. At Spaywar, I worked on the testing and research of the seawater antenna. The seawater antenna is essentially using water as a medium for the antenna rather than traditional metal. Advantages of this is the fact that the antenna could be turned on or off when in use, so the various antennas do not interfere with each other on the ships. Ships would then also require less antenna due to the fact that the frequency that the antenna operates at can be changed simply by varying the heights of the antenna. Another positive feature of the seawater antenna is we could effectively use a pump and a ferrite probe on a small ship to enable long-distance communication. So I have said this antenna uses a ferrite probe, which can be seen on the picture as this metallic structure. But what does it mean? So using a ferrite or metallic circular probe, we can then feed an alternating current to create a magnetic field. By using the right-hand rule or Ampere's law, we then have a magnetic field inside of the ferrite probe, which we then place a fluid like water. This fluid is then able to transmit an electromagnetic waves for communication. So, while testing for this antenna, I had a few things to determine, such as how do different types of water affect the antenna. So I used three types of water to test: tap water, distilled water, and salt water. Another question was, how does this relate to traditional metallic monopoles where the frequency can easily be calculated in correlation to the height, seen by these equations: L or length equals lambda over 4, and the speed of light over lambda equals the frequency that the antenna resonates at. So to compare these antennas, I tested them for impedance or VSWR. So what is VSWR? VSWR stands for the voltage standing wave ratio, and it is a ratio of the reflection coefficient. This is determined by the following formula, and by putting it simply, if the reflection coefficient is 0, then the VSWR equals 1, and no power is reflected. The opposite is also true, for when the coefficient is equal to 1, then the VSWR equals infinity, and all power is reflected. I tested the antenna in a PVC pipe, and the beauty of this is the length can easily be controlled by pouring water in and out of the pipe. The ferrite probe is then neglected, and the measurement setups were then fully facilitated. So calculating the properties of the antenna were then done by a network analyzer, as seen as the picture below. As you see in this graph, this is one of the VSWR graphs for some of the antenna, and by manipulating these graphs, I could then determine the properties of the antenna. So my testing setup, this is what my setup looked like, and it consisted of a pipe filled with water standing within a box for support. And by measuring the volume of the water inserted, I then can calculate the height of the functioning antenna. As a little refresher, I use three types of water: distilled, tap, and salt water. And by using a copper plate, I was then able to effectively ground the plane where the antenna was resonating at. So getting into my graphs and my data that I have achieved, this would be the first graph that I've created with water antenna at 12 centimeters. Traditionally, metallic antenna would resonate at around 586 megahertz. As we look at the graph of the VSWR versus the frequency in megahertz, we see that all three types of water resonate close to 586 megahertz over here of a true metallic antenna. All three water types seem to have a low VSWR, ranging anywhere from 4 to almost 1, with salt having the least amount of signal reflected. Saltwater also has a more stable curve, whereas distilled and tap water have a second resonance at around 1100 megahertz. We don't really see this with the saltwater, so we could kind of see that they have different agendas. As we increase the height of the antenna, the resonant frequency should drop, and this was validated in the following graph. When height was increased from 12 centimeters to a meter, we see a shift to the left for the resonant frequencies. At this height, the antenna should resonate at around 73 megahertz, and we see this very well with salt water, with a BSWR of 1.5. Little to no power is being reflected back at this frequency, and tap water and distilled water, however, only resonate between 300 and 1100 megahertz. We do not seem to see them resonate anywhere near 73 megahertz. From these graphs, we could deduce that the saltwater is a major factor in the fluid to make antenna resonate at given frequencies. Little overview and conclusion of the data. At UHF and above, all water types resonate like a traditional monopole. But at BHF, only salt water behaves like a traditional monopole. And the tap water and distilled water only seem to resonate at frequencies 300 megahertz and above. Other activities I'd done at SPAOR was I assisted with the measurements and testing of antenna brass model ships. I also aided in the tour of the model range for high school and college interns, as well as created posters and projects displaying the work done here at SPAOR Systems Center Pacific, and as well as a demonstration for the antenna for the Congresswoman Susan Davis, pictured here on the right. And in conclusion, the internship was very fun and many skills were obtained, such as learning how to use and calibrate network analyzers, calculating and understanding the characteristics of antenna, troubleshooting and determining how to make designs better, and creating and designing antenna. Acknowledgements would like to go out to AX Ramirez, Dr. Bakit, Kathy Tyner, and among the many who helped me at during the internship, as well as foundations such as MESA, SPAOR, of course, the Lip Family Foundation, NSF, and Southwestern College. And this whole internship would not be as well put without Daniel, Tam, and Diana Arceo as my mentors. Thank you very much.